Hey everybody. So we're going to do some work in this video, just a little introduction to start thinking about polar equations and graphs. Okay, so an equation, a polar equation, is the same thing as an equation in rectangular coordinates. You have these two variables r and theta, and you relate them with some mathematical functions, symbols, all that kind of stuff. And the relation between an equation and a graph is exactly the same. Remember, in a rectangular equation, for instance, if I write something like y equals x plus 2, the graph of this is a line because each point on this line, for instance, 0, 2, or let's call this 3, 5, those are x and y points that when you substitute the x coordinate in for x and the y coordinate in for y, the equation's true. Points that are not on this line, like -3, 1, don't satisfy that equation. If you put -3 in for x and 1 in for y, the statement's not true, right? So same thing with polar equations. That if you can think of graphs of them as coordinate pairs, but they're polar coordinate pairs that satisfy the equation. Okay, sorry, a little glitch there. So we've got a polar equation, and I want to graph this equation. And as I said, these are going to be the points that make this equation true. So if you remember maybe the first time you started investigating parabolas or lines, and one way you can start is by plotting points, right? So let's do that here. We're going to create a little table for r and theta. Okay, and I'll put in some values. So let's just start with, let's go with 0, pi over 6, pi over 4, and pi over 3. Okay, and so I'm just going to put those into the equation and compute what r is, right? And so these are all values from our unit circle. So for instance, if I put 0 in for theta, secant of 0 is 1. And so in that case, r is equal to 2. If I put pi over 6 in for theta, well, cosine of pi over 6 is root 3 over 2. So secant is the reciprocal of that. So 2 over root 3, and then we're multiplying by 2. So I get 4 over root 3. Here we'll get 4 over root 2. And here we'll get 4, right? So I'm just plugging those in using the values from the unit circle to evaluate them, and then of course multiplying by 2. Now, the meaning of these points, though, we have to remember, right? So just like with rectangular coordinates, if you plug points into something, you get an x and y. You know, x tells you where to move right, y tells you where to go up and down. We have to remember each of these coordinate points, what it means, right? So each of these is a coordinate point r0, r theta. This is our distance from the origin, and this is our direction. Okay, so on this set of axes with the origin in the center, this first point, which is the point 2, 0, is saying, well, point in the direction of a 0 radian angle, right? That's to the right. That's to the right by, that's to the right on the x-axis along the positive x-axis. And we want to go 2 units out. So I'll just put a little coordinate system or a little scale there. There's our point 2, 0. Right. This is one of those rare points that's the exact same meaning in rectangular, or same position in rectangular and polar coordinates, right? 2, 0 in rectangular coordinates land you in the same place, but then they'll start to look a little different. So our next point is pi over 6, right? So maybe I can, let's make that a little thinner. Right, pi over 6 is going to be something like this. Well, 4 over root 3. Root 3 is about 1.7, so this is a little bit bigger than 2. So we're going to end up with our point, a number a little bigger than 2 along this line, somewhere out here. Okay. In the pi over 4 direction, so that's more like this, we get 4 over root 2. So that's 4 divided by about 1.4. So that's almost 3 units along this line. And I'm just eyeballing things here. And then in the pi over 3 direction, something like that, we go 4 units along this line. Okay, so I'm eyeballing it. I may have an understanding of what this is supposed to look like, and we'll talk about that in a second, but it gives us some sort of notion of what this thing looks like, right? And the way I'm writing it, it almost looks like this might be tracing out a vertical line. Okay, so my dots aren't perfect, but it turns out this is true. Let's see if we can examine why. So let's first give an example. Let's look, for instance, if I think about, let's look at that last triangle we drew. If I take this line, this here, and this. So let's think about this green triangle that I just drew. Let's just move it out here. Ooh, that's terrible. Let's see if it fixes. There we go. Okay, not a perfect copy. So in this triangle, remember the angle theta is right here. This was the angle where we were going in the pi over 3 direction. So this is an angle of pi over 3. Okay. This is our hypotenuse, which was the distance we moved along this line, which was supposed to be 4. So I know that this is 4. Let's see what this distance is, okay? Our horizontal distance, okay? I'll call this distance A. Well, I know that the secant of pi over 3, the secant is going to be the hypotenuse over the adjacent side. In this case, that's 4 over A. I also know that the secant of pi over 3, well, we can get this from the unit circle, is the reciprocal of the cosine of pi over 3. Cosine of pi over 3 is 1/2. Its reciprocal is 2. So the secant of pi over 3 is 2. That means 4 over A must be equal to 2. And this is easy enough to solve to see that A is equal to 2. In other words, this distance in here is 2. And you can do that for each of the values I gave, and you can try some other values and realize that each of these values, the way this will work out, this R distance is always just enough to put us on this line, this vertical line, 2 units away from our vertical axis, okay? So it's the vertical line that in rectangular coordinates would be x equals 2, right? In rectangular coordinates, this would be x equals 2, right? That's a vertical line, right? We don't see y there when you don't see the other coordinate. If we're dealing with rectangular coordinates and I give you an equation without one of the coordinate variables, that means that that coordinate can be anything, right? So the equation x equals 2 is satisfied as long as x is 2, regardless of what y is. So anything on this line satisfies it. And it turns out this has the same relationship, this has the same set of points as its solution, even though the meaning seems very different, right? That the distance, in this case, the distance from the origin is equal to twice the secant of the direction from the origin, right? Which is a less obvious kind of notion, but turns out to have the same thing. We can also see that these two statements, x equals 2 and r equals 2, say secant theta is equivalent using, let's do this, using a little bit of algebra and our knowledge about the relationship between polar and rectangular coordinates. So let's look at this equation, r equals 2 secant of theta. Well, I know that secant of theta is just 1 over cosine of theta. If I multiply by cosine of theta on both sides, I get this. And if we recall, we have these two relationships relating taking polar points into coordinate points. Well, I can do this to my equation, saying that our cosine of theta is always 2 is the same as saying the x coordinate is always 2. And so we see that these two statements, right, algebraically, we're seeing that these two equations have the same meaning, right? And we see it graphically that they have the same set of points as their solutions, even though we think about them in very different ways, right? And here's a case where the graph of x equals 2, or seeing that equation, it's very easy to understand this equation, while this one is much more difficult, right? And this is often the case, that looking at a particular relationship through the lens of polar coordinates or rectangular coordinates might be very different. But in this case, the rectangular coordinates are much simpler. Okay, let's do one more example here. Let's start with a rectangular equation this time. Let's get some axes. Oh, I wanted 9. Sorry, not 1. Let's do 9. So first, let's think about the meaning of this, right? If I take, so points that instead of plugging in points, let's do this one a little bit differently. If I take points, if I take an x coordinate, if I take some point, I'll just put it right here. Its x coordinate is this distance. All right, let me begin this again. I don't want these little dashes because I might want to erase this eventually. Make it easier. So if I have a point out here somewhere, let's say it's a point that satisfies that. What's true about that point, if it has A and B, well, I can draw a little triangle, right? And if this is the x coordinate and the y coordinate, this will be A, this length will be B. What do I know about this? Well, I know, since this is a right angle, using the Pythagorean theorem, a squared plus b squared has to equal c squared, whatever the length of this is. But we already know that a squared plus b squared is equal to 9 if it satisfies this equation. In other words, the distance, the hypotenuse, has to be 3. Okay. And if there's a different point on this little triangle, or that I say satisfies this, it still has that relationship, right? Whatever this side here is, let's use different letters. Let's call this, I'll just call it capital A, capital B, if this is the point, capital A, capital B. Those two still have to sum, the sum of their squares has to be equal to the square of this distance, this hypotenuse, so that'll be 3. And even if we go in the negative direction, so if I did like negative A, negative B, this will still hold because the squaring gets rid of the negative. So even if we're going in the negative, B direction here and negative A here, when I square those and sum them together to get 9, it gives me that this distance is equal to 3, right? So all the points that satisfy this, I can make this little triangle. So it's kind of like saying it's these vertices of every triangle whose hypotenuse is 3. That's the set of points here, right? Well, maybe a more convenient, a less awkward way to think about that is that hypotenuse is just the distance from the origin, right? For each of these triangles, it's a point that's that far away from the origin. I know my pictures aren't perfect. They're not all exactly the same, but imagine that they are. So it's really the set of all points that are 3 units away from the center, which you might recognize as being a way to describe a circle. So let's get rid of this and draw that in. Oops. Let's do this. Well, I'll just redraw it. It was a valiant effort, if I do say so myself. So this is going to end up being a set of all points 3 units away, right? So I'm drawing what I hope to be, let's just put in 1 point. All right, so that's our circle. That's 3 units away from the center. And you might have recognized this already as the equation of a circle. Okay. How would I describe that same set of points in polar coordinates? Well, remember a minute ago when we thought, well, the line x equals 2 describes a vertical line where we don't care about what the y coordinate is. All we care is that the x coordinate is 2. In other words, all we care is that it's 2 units to the right. Any point that's 2 units to the right of the y-axis satisfies this equation. We want to do a similar kind of thinking here. We want all points whose distance from the center is 3. Well, when we give polar coordinates, this is our distance from the center. This is the direction. So all that has to be true in polar coordinates is that the first coordinate is 3, and theta, the direction coordinate, can be anything, because I don't care if it's pointing here, I don't care if it's pointing here, I don't care if we're pointing here, right? Any direction works as long as it's 3 units away. And so this theta is just like y over here. It doesn't matter, it doesn't show up in the equation. The polar equation of this circle is simply r equals 3. Right? Same reason y doesn't show up here. I don't care what theta is as long as r is equal to 3. Okay? So we reasoned our way into that, but we can also think x squared plus y squared equals 9. How do we convert, if we're given some rectangular coordinates and we want to convert to polar, remember we have the relationship x squared plus y squared equals r squared. We also have that theta equals tangent inverse of y over x. I'm just going to put a little asterisk here. Remember, if it's in quadrant 1 or 4, this is true. If it's in quadrant 2 or 3, here, I'll do it this way. Sorry, there we go. Let's do it this way. This is the equation for quadrant 1 and 4. We have to add pi if we're in Q2 or Q3. Okay, so you might have to add pi depending on which quadrant. But the important part for us is this x squared plus y squared equals r squared. So if I want to convert this to polar, I can replace x squared plus y squared equals r squared. This gives us 2 equations, plus or minus 3. So r equals 3 or r equals negative 3. But they both describe that circle, because remember, if r is negative 3, all it says is point in a direction and go backwards. So now this line here, for instance, that's pointing this way and goes 3 units that way, if we pointed in this direction, we would just go 3 units in the opposite direction and land on the opposite side. And so since we're going in every direction anyways, we'll still hit them all. It's just we'll hit them in that weird way of pointing this direction and taking 3 steps backwards. Okay, so we typically just take the positive when it doesn't matter like this and take that as our equation. Okay. Okay, I think that's it for the introduction. Just get to start thinking about polar graphs. We'll do more examples, but that's it for now. Thanks, everybody. I will see you next time.